the one we're having now in January with our visitor, Gabriele.
Yeah.
Please take it away.
Thanks. My name is Gabriele. I'm a PhD graduate student at the University of Arizona, and I'll be here today and tomorrow. And as I already told many of you, I will absolutely love to chat with you. I'm in the 4th floor, somewhere next to the staircase. Please come and talk to me. We'll be super thrilled to just chat with you. So with that out of the way, today I would like to give you, I don't want to give you a seminar. What I want to do is I want to lead a discussion about the high energy collision of particles. We're going to start with something else. And that's why I'm using a blackboard, because I have an idea of what I want to tell you, but I will be very sad if I were to just follow my notes. So please interrupt me, please ask questions, please make comments. I can take this anywhere you want to go, and we can talk about something that you find interesting. So again, I very much welcome interruptions. So please do so. So yeah, today we're talking about high energy collision of black holes. And our story starts in 1971. 1971 with Penrose. And Roger Penrose, Nobel laureate, everyone knows here, I'm super sure. And what Penrose and collaborators noticed is that if you take two planar gravitational waves and you make them collide, so you have a system like this, planar gravitational wave here, planar gravitational wave here, you make them collide, what you get again here is a naked singularity. And naked singularities are going to be important today. Naked singularities in many ways are the common thread that are going to be at the foundation of the talk today. Naked singularity that I define very simply as a region in our manifold, as a point in our manifold where we have a singularity, but we don't have any horizon to protect it. We don't want naked singularities. We don't want naked singularities because determinism will break, our physical theories will break, and as famously Stephen Hawking said, nature abhors naked singularity. We don't want it. But here we already have a case with gravitational waves, planar gravitational waves, where we can form a naked singularity. But people were not concerned with this. They were not concerned with this because this is extremely fine-tuned, an extremely artificial case. Well, for once, we have planar infinite gravitational waves. The space-time is not asymptotic. There's infinite amount of energy in here. Essentially, what's happening here is that the two wavefronts are focusing each other into a single point. We're dumping an infinite amount of energy into a single point. This is not something we expect in nature. This is a beautiful, but very much artificial example. Yes, we can break our theories, but it's not something that people were concerned about. But shortly after, Penrose, still in the 70s, tried to refine this idea of having wavefronts that collide to form a naked singularity. But instead of having wavefronts, the idea is, what if we take something like a black hole and we boost it with in the limit of infinite speed, where infinite Lorentz factor, so it's speed that goes to the speed of light. So we squish it on one side, and what we're doing is taking our horizon and make it thinner and thinner, so concentrating a finite amount of energy in a very, very thin, ultimately something like a waveform, a planar waveform, and make it collide. So once again, we have a collision of our two horizons with approximately infinite speed. Can we form a naked singularity here? Can we reproduce what we had without some of the pathologies that we had here? So Penrose couldn't answer this question. And what he did was, however, was to find some interesting theoretical, analytical expectations about this case. And for instance, what he found is that the energy lost in the emission of gravitational waves as a function of the initial energy, which now is finite, has to be bound by a value that is 29%. So almost 29% of the energy in our system can be lost due to emission of gravitational waves. But Penrose couldn't answer the question, what is the end state here? We don't know if the Penrose didn't know if that was a naked singularity. And shortly after Penrose, we had very smart. They refined some of these calculations in a specific approximation called the zero frequency limit approximation. And what we found is not only something like this, but we found a specific functional form for EGW as a function of initial boost. Now, this is an absolutely horrible formula. I don't remember. I'm going to make it up. It looks like this. Rule gamma squared plus 1 over gamma plus b plus small square root of gamma. I have no idea. It's awful. But what it looks like is the following. Here we have gamma. Here we have the fraction of energy plus conditional gravitational waves. And look at this. So it's bound by a value that we call infinite, which Smart couldn't compute, but it has for sure is more than 29. And it looks like this. It's finite. We cannot lose 100% of our energy. And there's an expression which I completely made up here. I don't remember. It looks like this. That is computing a specific approximation, the zero frequency limit approximation. And I'm still amazed by the result by Smart that not only found this, but even found the amount of energy lost through each single multipolar moment. So we have an expression for this as well, which is crazy. But that was the state of the art in the 70s. For 30 years, essentially there were no advancements on these fronts. We didn't know if we could form naked singularity in these cases. We didn't know what is the value of this image. And here it was bound by 29%, but well, we don't know the value. We didn't know if this formula was a good approximation or not. There was lots of questions in this area. But I think that Smart and Penrose reached the limit of what analytical methods could do. And for those of you that are expert, the techniques used here, these are so-called eigenforms, so type of waveforms, type of spacetimes that describe essentially boosted particles at the speed of light. It's very technical. And what we needed here to continue in this line of research was the breakthrough in numerical relativity in 2005. So in 2005, starting with Pretorius, as a community, we'll learn how to simulate black holes and solve Einstein's equations, the binary black holes and solve Einstein's equations. So Pretorius, for the first time, simulated quasi-zero going spirals. And shortly after, in 2008, then we have a paper by Luis Ferrate and al. called the high energy collision of black holes. Friday, it's the same. Where for the first time, we have new results in the context of the high energy collisions. So finally, we can say something more. But not only we can say something more, we also have new questions. Because in these 30 years, new fields of or areas of physics essentially developed. New questions arose. So here I'm going to use this cute little board to summarize the questions in this line of research. So first of all, our common thread formation of naked singularity. Second question has to do with the energy lost in the process. And this is not only to check these calculations, to calibrate those calculations, but people started being interested in the maximum energy or the maximum luminosity that any physical process may have. Sometimes people call this the Dysons Luminosity. I'm going to write it down, knowing that this is wrong. Wrong in the sense that Dyson never thought about this. Unfortunately, this is a name that's stuck, so I'm going to use it. Why is it called Dyson? It's called Dyson because it's mistakenly attributed to a paper that Dyson didn't write. I mean, Dyson wrote a paper for a chapter of a book in which he talks about something related to this, but it never conjecture what I'm going to introduce in a second. But people, I don't know if they misread the paper or they just cited papers that decided to use this terminology. So this name stuck. So you're going to find it open. I'm going to use it because people use it. But again, Dyson never described what I'm going to describe. The idea of Dysons luminosity is the following, is that we have some constants of natures. We have 1 that is equal to h bar, c. And these concepts of nature, if you mix them in a specific way, you can compute a luminosity, which I think it's going to be for C, I don't remember. But in these units, this is fine. And according to the idea of this conjecture, Dysons Luminosity, is that there's no physical process that you can think of or that you can come up with that has luminosities greater than this. So the Dysons Luminosity, the idea of Dysons Luminosity is bound by this value approximately in natural units. Now, I'd like to tell you about what's our state of understanding for Dysons Luminosity. And I'm going to raise the board for that. Thank you. By the way, let me know if this is too small or my handwriting is messy, it's incomprehensible. I'm going to pretend I'm going to fix it, and in 5 minutes later, again the same size. So right now, the highest luminosity process that as mankind we managed to produce is the Tsar Bomba. So which is the largest nuclear bomb that the Soviet and humans ever produced. And I think in natural units, this is order of 10 to the minus 26. So we're quite far away from being able to produce an extremely energetic system. We're getting much closer with binary black hole spiral. So the processor spiral binary black hole. If you fine tune it a little bit, we spin this type of stuff. I think the best we can do is order of 2 minus 2 and these units, which is getting close to 1. But the record holder that is going to come back in a little bit is the critical collapse. Now, in a critical collapse, we consider some form of field with a total energy. And if we tune the energy in a specific way, we can have essentially a critical phenomena. We can be at the boundary of dispersion of the field or collapse into a black hole. And the critical collapse, we can do order of 10 to the minus 9. So this is the record holder for the process with highest luminosity that we could ever conceive, if you want. So far, Dysons Luminosity seem to hold true. And in this, we're also interested in how much energy is lost as a function of energy, as a function of the initial energy. And this is also because in the 30 years between Penrose Smart and 2008, there started being interest in the so-called TeV gravity. Now, once again, I'm going to use my constants of nature. I don't need it anymore. I'm going to use my constants of nature to define a scale. It is the Planck scale, which I think is about 8 parts over G Newton. Now, if we plug our usual, well, my units is 1, but if you plug your SI or physicist units, and you plug your usual 6 to the 10 to the minus 11 CGS, this is order of 10 to the 9. So this scale is absolutely insane. We're to build an particle accelerator with a scale of and this is technical energy, is not mass, but we understand each other. If we were to build an accelerator to reach this energy, we'll have to make its radius to be order collective radius, so 1 kiloparsec, 10 kiloparsec. We cannot do that. But in the 90s, early 2000, people started realizing that maybe this is wrong. This is not really the correct scale that we have to look at if we want to think about quantum gravitational effects. So the idea of Planck's mass is that this is the scale at which we have electroweak strong and gravitational quantum unification, or this is a scale at which we should expect to see quantum effects with gravity, or gravitation effects with quantum behaviors. So what if G was wrong. Or this jet was actually a four-dimensional projection of a real G that is actually due to a much larger number of dimensions. So what if we don't live in a four-dimensional spacetime, where we live in a 11th, 10th, 26th dimension? Up to you. You can pick whatever mechanism you want. You can pick a Randall-Sandrum mechanism. You can pick a Booz-Klein type of mechanism. In the late 90s, early 2000s, people started thinking, okay, what if we change G to something that leads to a Planck mass of order of TeV? And why do we want to have a Planck mass of order of TeV? Well, high-energy physicists were interested in Planck mass of order of TeV to solve the hierarchy problem. And the hierarchy problem states that there's something weird with the fact that gravitational scale is completely off the chart compared to the electroweak-strong scale. There's also maybe a fine-tuning of the physical parameters to which, so that we get this like very weak gravity as opposed to everything else. The hierarchy problem essentially looks at all this number and says this gravitational one seems to be odd. There's something weird there. And allegedly, I'm not an expert here, absolutely, but we solve the hierarchy problem if we set the mass scale, Planck's mass scale to be order of T. But this is also interesting implications, because if the Planck scale is order of TeV, then our experiments, like the Large Hadron Collider, can actually detect quantum effects or gravitational effects with quantum effects. The Large Hadron Collider right now, I think, is running out. And it was exactly 2008 when the Large Hadron Collider, for the first time, reached the TeV scale, 7 TeV, I think. Now, probably you remember, but people were very, very, very worried that LIGO LHC will produce black holes that will kill everyone. So I typically show this plot, fun digression, just for the sake. So number of surfaces of black holes, Google, and here. Now we have, for us physicists, 2015 was a very important year. We had LIGO, the announcement of binary black holes, merger of binary black holes, and even got the front page of New York Times. So indeed, it was a spike, but this completed work. So people were a little bit more worried about dying than binary black holes. But yeah, so this is a very interesting possibility. Is that we can see production of microscopic black holes. We can see micro effects of again some quantum gravity type of effects in the Large Hadron Collider. And if this was true, indeed, essentially what we'll have that's LIGO. Sorry if I keep calling LHC LIGO. LHC will be like what people sometimes call trans-Planckian machine, because you will reach energies that are larger than the Planck scale. So this is sometimes referred to as trans-Planckian regime. And where in that case, we'll have the gravity starts to be important. We have to study the gravitational interaction of particles that will essentially be black holes to understand what LIGO sees. And that's why we also want to look at this. That's why I want to see, for instance, cross-section of black holes and their emission and their spectra, so that we have a better sense of what will happen in a particle accelerator with production of microscopic black holes. So this was another development in the years between Penrose and 2008. And there is something that is connected to this. That is another conjecture that I particularly like, because there's a very catchy slogan that is matter doesn't matter. Okay, according to this conjecture, if we are considering a system that is dominated by kinetic energy, like ultra-relativistic collision of black holes, then you don't really have to worry about the internal structure of the colliding object. You don't really have to worry about the properties of the colliding object. All the observables are going to be the same, which means that if you're colliding particles without spin, you're going to get the same as if you're colliding them with spin. If you're colliding them with a different mass ratio, if you're colliding boson stars, if you're colliding neutron stars, if you're colliding solitonic waves. The idea that matter doesn't matter says that the dynamics and the observables are always going to be the same, no matter what. And once again, this feeds into the previous points, because in Monte Carlo generators used by a Large Hadron Collider, this assumption is used to ignore some of the parameters. We just have to look at the most basic case to have some observables for every single case. Now, the idea that matter doesn't matter, according to some, is very surprising, because the structure of the spacetimes is quite different in the limit in which ultra-relativistic limit. Now, I don't know the details, but intuitively it makes sense. And I'm going to use part of my time later today, to justify on physical grounds why this is a good idea. And I think that will bring me to start discussing chart. Let me see if I missed any other motivation. In the meantime, you can think of a question, because you're being a little bit too quiet here. Okay.
For sure that we already quite looked at
yeah.
Gravity is basically on $1.
Yes. So I'm going to, before moving to charge, I'm actually going to discuss a state of the art or results before that. And that's one of the results, is that we're still here. No microscopic black holes followed us. So we have zero evidence of TV gravity. I would also like to mention that with all the Large Hadron Collider is like a good place to look for microscopic black holes, but even better, cosmic rays, because we can reach much higher energies there. So there's no evidence for microscopic black holes in cosmic rays. There's no evidence for microscopic black holes in particle accelerators. There's no support for TV gravity at this point. So people are still interested in that. You can always tweak your models in some ways to make it relevant. But yeah, it seems that that's, I don't know if it's a dead end, but people are not as much interested in that as before.
Can I ask you something related to this extra dimension thing? So it's not clear to me, because when you say that G Newton could be like embedded in some extra dimensions, but then when you want to study your physics in 4 dimensions, you have to do some dimensional reduction, and then I expect that m Planck squared to enter your effective action, and that should be actually a scale that is relevant for gravity. It should not, I mean, that we can test with experiment.
Yeah. Yes, I don't know the details. I think maybe what I should say is that the actual scale of quantum gravity, I should flip this things around. I was supposed to say this is a projection. I should say that the actual scale which we have the trans-Planckian regime is with the actual G Newton, as opposed to the opposite. I don't know, does it make sense? Maybe yes.
Okay.
Yeah, if I flip things around, I agree, our experiments do see the G Newton that we see here. It's not what it is. So I should flip the things around. Okay. Thanks, that's a very good point. Okay, so well, right now, the benefit of 50 years of work, we know that the gravity is not open, but in 2008, people were very much interested in that. And I would like to tell you something about, well, I already told you about Dysons Luminosity. I would like to tell you something about naked singularities first, before we move on. First, I would like to tell you that we can form naked singularities. Well, I showed you one example, but that was kind of fine-tuned. We can form naked singularities in the larger than form. It's not particularly difficult to form naked singularities in the larger than form. You don't need super fine-tuned data. I think you don't even need simulations here. I think you can take a black string and pinch it, and you get the formation of you get the black string breaks apart. So yeah, we can form naked singularity, but I like even more that we can form naked singularities in equal form, and we can use the same mechanism that I told you before, being the record holder for energy luminosity, this is the critical collapse. And this is one of my favorite things ever in physics. So it's completely I don't know if there's a C, 1993. So famously, Hawking, Preskill, and Thor made a bet, say it's impossible to form naked singularities dynamically. To show that indeed it's possible, again, if you take this collapse and you fine-tune the initial data so that you're in the threshold between dispersion and collapse, you can get deformation. Now, Hawking indeed conceded the bet, saying that he lost, but he made a new bet saying that you have to give up the idea of fine-tuning of initial data. In the sense that for general initial data, we cannot form make a singularity. So yes, in '93 already we knew of a case that was informed by numerical relativity where we could form naked singularities. So maybe it's worth looking at again in the case of ultra-relativistic hadron collision if we can form naked singularities there. So there was a case in which we did that, and now with the study in 2008, we can answer that question. We can answer this question, or give some more info to this question. We can start addressing this question. And well, in gravity, we can already ignore that. So in 2008, there was our first study. It was enabled once again by numerical relativity. Two black holes colliding one against the other. It's an axisymmetric system. And what was found is that there was no evidence whatsoever of formation of naked singularity. So it seems in our simulations with the gamma that was used in that case, which was like gamma was 3, not super high, but as we're going to see, we don't need very high gammas for these studies. We cannot form naked singularities. The second result is that we now have a better handle on what is the energy lost in this process. Before our expectation was less than 29% from Penrose. Now we know that it's, or in 2008, what we know was 14%, I think plus minus something like 50%. So now we also have that we calibrated this and later studies, I think in 2013, by refine this number, I think 13% plus minus 1%. Here you have to be careful with initial data, constraint satisfying, resolution. So we understand pretty well now, I think, what is this infinity over EAM. Actually, not this was. And for 2008, we started, well, the community started running more and more simulations, looking at more and more systems to say that indeed we'll get the same observables. And same observables, for instance, means what is this volume? And also, what was found already in 2008 is that our ZFL estimate is actually pretty good. The ZFL formula works reasonably well works pretty well to describe the energy lost as a function of our gamma. So SMAR was pretty much spot on in the expectation for infinity and for the functional form for the energy loss as a function of our initial boost. So later, we started running more simulations.
Do you remember what the largest gamma factors were?
Yes.
I think in the least papers, like the biggest they can manage is like.
Yeah, exactly. I think no, I think it's pretty much the same. I think it's order of 3.
So
Yeah.
I think there would really be space to try.
Yes.
You know, there's
Yes.
a big range between 4 and infinity.
Yes. I
It
agree.
might be worth doing like
Yes.
coming up with improved initial data. and
Yes.
pushing that.
I agree. Let me just mention that it's a challenging type of work because you have, with the larger the boost, well, at least 2 reasons. The larger the boost, the more resolution you have to throw, because if you want, you can think about contraction. So you have to throw more and more points to restore the size of the black hole. And second, at least in my simulations, as we mentioned initial data, I cannot push my black holes much because they're not. My initial data is not a good description of the system. So as soon as I try to push my black hole, they slow down. So I cannot physically reach very high gammas, and that's so you have to engineer initial data much better. So yeah, so we had the confirmation that the ZFL limit works quite well, and yeah, as I was mentioning, we started getting more and more evidence that indeed matter doesn't matter. So that's the state of the art. And now I think I'm going to start talking about why I think that including charge is a very, very interesting thing to do. But first, maybe you can ask me any question. Okay. I'm going to erase the parentheses here since I'm going to talk about that. And okay, now charge. Charge is interesting. If we think about spin, if we think about mass ratio, if we think about all the stuff that people tried before, they weren't fundamentally different from black holes. There was no new channel. Like when you have charge, there's a new emission channel. You can radiate energy through electromagnetic waves. There's no new conserved quantity for the most part. But when you have charge, you have to conserve charge. So introducing charge is a fundamentally new system. It's different from what was done before. Now I'm going to trick you and giving you an argument that I know will not work. And I'm going to tell you, I'm going to show you that maybe there's some problem in some of our fundamental ideas that we really like. For instance, the idea that charge doesn't matter. So if this is true, if matter doesn't matter, then does charge matter? And the second, I'm going to go back to make a singularity. Can I form? These are my two questions, and I'm going to answer in the next 25 minutes. Can I form a naked singularity? Okay, so why it's interesting? Why it's interesting to look at this, and why maybe there's a problem. Well, let's consider two factors. One more bit of information before I start is so we have theorems, uniqueness theorems that tell us that the most general stationary symptotic flat spacetime is the current Newman spacetime. Electrovacuum spacetime is the current Newman spacetime. Current Newman spacetime is described by the mass, the spin, which is defined as angular momentum, or mass, and a charge. Now, I'm using units in which these are all the same, like the same in the sense of I measure them the same units. So I measure the spin in units of mass, the charge in units of mass. If you're not familiar with these units, especially for EM, Q over M for a proton is order of 10 to the 18. So this is a statement, electromagnetism is much, 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 much stronger than gravity, once again. But for black holes, there's a relationship. It tells us if we want to have black hole, so if we want to have an horizon in this spacetime, we have to have more mass than charge. If we overcharge or overspin our spacetime, we're going to lose our horizon. And since I'm going to consider x-symmetric mergers, I'm going to ignore the angular momentum part. So what I get is that Q over M has to be smaller than 1 to have a black hole. And once again, this is the most generic spacetime, stationary spacetime that we can have under these assumptions. So what I'm going to try to do is I'm going to try to make Q over M larger than 1. And what I'm going to do is this. I'm going to start with 2 black holes, make them collide. But this time I'm going to give them a little bit of charge. So I'm going to have a Q and M, Q and M. Of course, at the beginning, Q over M has to be smaller than 1 because we start with black holes. But then, if charge doesn't matter, then in the limit of infinite boost, then we know that the M final is 86% of the M initial. because we had our 14% for the emission of gravitational waves. So I'm part of the smaller, well, the strictly smaller condition. Not only that, it's interesting to say, well, if charge doesn't matter, it means that in the limit of infinite boost, there's no electromagnetic emission, because otherwise there will be an observable that we can detect, that will be used to tell the two systems apart. So charge will matter. And this is also interesting by itself, because as a numerical relativist, when I think about gravity, I actually think about electromagnetism most of the time. I use E and M as a way to get understanding of what the full nonlinear theory does. So I very often think of one as a proxy for the other one. But here there's a fundamentally different regime in which the electromagnetic emission has to disappear for this to be true. So yeah, so we have less energy that we started with, but charge has to be conserved. We cannot radiate away charge. Electromagnetic waves nor electromagnetic waves carry away charge. So Q final is the same as Q initial. So can I get that? Q over M larger than 1. If I start with larger than Q, can I, because I have a smaller energy, but I keep the same charge, so maybe I can fix this. And since the system has to relax to a Newman spacetime, maybe that's a way to form an existing glove. Now, I gave myself away, but I knew that there's a flaw in this argument, and I'm going to already tell you that unfortunately, in spite of all my attempts, I cannot form things. And charge, actually, it doesn't really matter. So now let's see why. So instead of creating suspense, I gave you the answer, but I want to emphasize a little bit of physics that's behind here. So first, the first piece of evidence comes from the case with gamma equals 1. In the case with gamma equals 1, now let me take any gauge invariant quantity, for instance, gravitational waves. I'm thinking about psi4, if it doesn't matter. In the case with gamma equals 1, this is what I have. I have my, let's start with I'm going to use y for Q 0.4. Okay? This is loop right. This is my gravitational wave. I'm going to put a little bit more charge on H. One good step. Now let me put even more charge, like 0.99. So in the case with gamma equals 1, as we can see from my neatly drawn plot, charge matters. My observable, which is measured very far away from my system, does depend on the configuration that I'm working with. So charge matters in the limit of flow energy. But then when we can see in a maybe easier way to look at that emphasizes something else. Sorry about that. If I instead of looking at this quantity, I look at quantities I can draw a little bit easier. The coordinate distance between our two horizons. We have our charge of 0.4. We have case with more charge. Case with even more charge. So here, so this is the coordinate distance between the horizons. Fine. I get that clearly it depends on the charge. Now, interestingly, there's a rescaling that I can perform. A rescaling because of the function of 1 over Q over M to some power of alpha, where if I scale in P, so I can say the alpha is to this, and the numerical I have to rescale B, but it doesn't matter. If I just do this rescaling, all my signals are going to be exactly the same. So not only charge matters, but it matters in the limit of energy in a way that we can understand very, very, very well. Because this was predicted beforehand, and this work by Yao, 2012. You can understand this very well. And in a nutshell, this comes from essentially when you have charge, you're reducing the effective gravitational force because there's electrostatic rotation.
Is movement distance here proxy for distance?
yes and no. I'm showing you coordinate distance because I can draw this easily, and this works well. The same is true for psi4. The same is true for other gauge invariant quantities. So I don't know if it's a gauge invariant. It's not indeed. That's why. But I show this because it's a little bit easier to compute and visualize. And but the statement I'm making that you can use a rescaling and get a perfect match works for gauge invariant quantities. So I cannot answer that, but this is right. So yeah, so in the case of low energy, this works very well. We understand it very well. And again, it's essentially due to having less gravitational attraction, if you want. But now it's my time, the time in which I run my simulations. I look at the case with the limit of higher gamma. And now my higher gamma is actually 1.2. Not particularly high, but already at 1.2, something amazing happens. At 1.2, and again, here I'm looking at the distance, not because it's gauge invariant, but because it's easy to draw. If I ignore any rescaling, if I just plot all my various quantities, I get exactly the same for distance, for psi4, for time of formation of common interplanetary horizons, all the gauge invariant quantities that I look at, without any rescaling, they are identical. This provides support that charge doesn't matter. It doesn't matter for radiate gamma at 1.2. And I can, for instance, I can look at the energy loss, total energy loss, because now we have also electromagnetic energy, a function of the initial energy. We had our ZFL formula, and my simulations are right where they have to be. And there's no emission of electromagnetic waves. So numerically, I can see that the charge doesn't matter. But now let's understand that. Because that's why I really like this. Because we can understand this. I convinced myself that I can understand why this is happening. And I convinced myself why this is happening already this slow down. And I think, let's see how we go to the time, but that might be the last point I have here.
Gabriele, sorry. So that would also be the case for gamma larger than 1.2.
Yes.
So from there onwards, you should expect.
Yep. So there's a threshold gamma with to be high energy, and this is a very, very low gamma. And now we're going to see that it is not surprising. And this is also going to, if you want to shed light on why it matter, doesn't matter. At least my personal take on this business. And for this, I'm going to go to let's say toy model or simplified understanding of the problem. And I'm going to consider two values, one here and one infinite far away, which I'm going to draw here. Mass m as charge q. M. I'm going to take them identical, so it's easier. In the limit of infinite separation, and I'm going to give them initial boost gamma. Axis symmetrical collision, again, to keep things simpler. At the beginning, if you think about classical mechanics, Newtonian mechanics, if you think about, for instance, the Hamiltonian or the Lagrangian, there's two terms. There's the kinetic term and there's the potential, the interaction term. At the beginning, the kinetic term is much larger than the potential term. Because in the limit of infinite separation, the interaction term is 0. But in general, at the beginning of our interaction, what matters is only the kinetic term. And here, once again, I'm going to use some like classical-ish equations. So the kinetic energy in our system is gamma. Yeah, because we have two equals. But then, at some point, our interaction term is going to be important. And here, let me focus on the electrostatic interaction term. We're going to have a E potential. It's going to look like Q squared over Z. Let me put some squiggles. Importantly, the interaction term is of the couple, and they can get the terms of the sum of the two. But actually, it's not really important, but I mentioned that. Now, if these were particles, normal particles, what will happen is that we start with a very high kinetic term. The particles get closer and closer and closer. At some point, E potential is going to be comparable to E kinetic. This term is going to kick in. It's going to be repulsion. Particles go back to infinity. That's the end of the story. So we can define a length scale, dEnm. The dEnm is the length scale at which the electrostatic interaction starts to be important. So for that, I'm going to compare these two terms. So I'm going to set them, to be approximately the same. So dEnm, what I have here, is going to be Q squared over T gamma. Once again, if these were particles, they will reach dEnm, and they will go back. These were black holes are not particles. There's something fundamental in generativity or in relativity that is that we have there's a causal structure of our spacetime. There is a causality that we have to obey. There are horizons where there cannot be information that propagates outside of the horizon. This concept of horizon is really critical here. And here, what I'm thinking is, for instance, the Hooke conjecture. The Hooke conjecture, which says that if you put too much energy in a small space, you have to have an horizon around it. So there's not only this dEnm, there's an additional length scale in the case of black holes. This additional length scale is GR. This length scale on which relativistic effects start to be important, where the fact that these are black holes and not particles start to be critical. And here I'm going to estimate dGr to be approximately, once again, the total energy of my spacetime, which again, we start with this. There should be some loss of energy, but I'm not going to ignore it. There's going to be 14% in the limit. So this is one is MPDM. And if you want to be a little bit more precise, there's probably factor 2, but who cares? When black holes reach this distance, I pack so much energy in so little space that I cannot go back. I cannot break my two horizons apart. Horizons can only merge, cannot bifurcate. When my particles reach dGr, then that's the end of the story, then that's the merger. So now what I can do is this. I can compare the dEnm with dGr. So now I can compare dEnm. Yeah. Yes. And then I have our probability squared. Now Q of n. This is always smaller than 1. So this is probably always smaller than 1 over beta. Now, it doesn't take very high gamma to get dEnm is much smaller than dGr. So with relatively low gammas, what happens is that dEnm is much smaller than dGr. What this means is that the length scale at which interaction starts to be important is after merger. It's too late. There's no information that can propagate outside. This is the details of the interaction only matter when they don't matter anymore. Only matter deep inside the merger where nothing can escape. And that's why charge doesn't matter. Have already small gamma, because it will matter only too late again. And that's why it's true for not only charge, it's true for any type of interaction. This side. For spin interaction, you would get probably a factor of 3. I think spin interaction is cubed. So this even works. So no matter what you collide, as long as you have a generativity, as long as you have a kinetic dominated type of interaction, you're always going to get something like this, in which the details of the interaction matter only essentially after merging. So what I'd like to say in this case is that, again, the causality structure of our spacetime is an even stronger force than ENM. We have to have horizons to protect our singularities and to keep information where it should stay. And that's why charge doesn't matter. Any comments on this?
I have like, what happened with the story of the charges being like total charge being above total mass?
Yeah, that's the second question. So I was going to go into that. Okay. So if you're convinced the charge doesn't matter, then now Now we can take the next step, and we can see why I cannot form a single item in this case. And for that, once again, I'm going to hang on physical principles, and the physical principles I'm going to hang on here are conservations. So the energy has to be conserved. So my initial energy, M in M, we do M. Well, this is conserved, which means this is going to be M final. This is the energy of my remnant plus energy lost through emission of gravitational waves plus energy lost through emission of electromagnetic waves. There's nothing else. Here I accounted for all the type of energy. Well, charges to be conserved. So Q final, that's the Q initial, which is 2, 2. Okay, now I can compute Q of M. Well, Q final is 2Q. Now here I have W. Oh, yeah. Oh, no. So this is, I'm going to, so I want M final, so move these around. Actually, M again. Minus CGW. Minus CGM. So I'm going to group out M again. Now, I'm going to erase this and substitute this with our 2 gamma. It doesn't matter. Now, for gamma large enough, we established that charge doesn't matter. So when charge doesn't matter, this doesn't matter. When charge doesn't matter, this EFL limit is a good description. So I can substitute instead of here, I can substitute my function C of lambda, which is a horrible function that Mar gave me 52 years ago. So what I can do is I can plot this. I have as a function of Q over M initial. So I can plot Q final over M final as a function of gamma. And this is what it looks like. Here I have my gamma. Here I have my, let me call this lambda. Lambda. And this is what it looks like. So our limit is 1 here. We want to go above 1, but we cannot do it. And now I have this theoretical expectation. If I were to plot my simulations, because I can compute this from my simulations are doing very, very well. So now let's understand what's happening here. First of all, we can see that we can never cross the bound of 1. So we cannot make a single lattice. Actually, the higher the gamma, the less, the further I am from permission of a single lattice, the smaller is my final Q over M, which seems counterintuitive. But now the trick is this. The trick is in this. When I increase my Lorentz factor, I'm essentially pumping more energy in my system. The higher the gamma, the more kinetic energy in my system. And at the end, this energy has to go somewhere. And where it goes, it's in the remnant. So the more kinetic energy I have, the more kinetic energy ends up in the remnant. So it dilutes the Q over M. So that's why it gets less and less and less and less extreme, because I have more and more and more energy that at the end I'm going to capture in my remnant. So maybe we should be worried about this. We should be worried about the case in which I have gamma equals 1. In that case, maybe that's where I can form a situation. But once again, this was solved by Zilhao in 2012. And it was found that there is no evidence. And the nature is it's fortunately too clever for us, and the emission of electromagnetic and gravitational waves is such that once again we're always going with gamma or with Q over m it's more than 1. So yeah, I cannot form naked singularities, and the reason is yes, charge is conserved, but there's more and more energy available in my system. And now I can unveil my trick in setting up the experiment, the conundrum, where I tricked you and where I tricked myself for a long time. So I solved the problem and understood where I was doing wrong. So when I discussed my two black holes here, and I told you about M and Q, and when I told you about the increase in value of gamma, well, when I was increasing the value of gamma, I was actually increasing also the kinetic energy in my system. So to be a little bit more precise, what I would have done, what I should have done, is to keep some M constant. So I should decrease the value of M every time I increase gamma if I want to keep the energy fixed. But when I do so, at some point I'm going to have Q over M larger than 1. So I'm going to start with naked singularities, which is not what I want. So if I keep this fixed, to keep my total energy fixed, then at some point I cannot generate initial data anymore because those are not physical. So that's why that was the story of my research here, is understanding why my argument was wrong. And I hope I also tricked you in believing that my argument was right, and now I'm showing you why my argument was wrong. So with that, I think I told you what I wanted to do, what I want to tell you, and I'm going to take more questions if you have. Otherwise, I'm going to emphasize again that I would like to chat with you, so please come and talk to me.
Do we have any more questions from the speaker?
I was wondering if you could clarify a little bit when you gave your estimate of the DGR.
Yes.
Yeah. So they said that it's 2 gamma m.
Yeah.
And so my question is,
yeah,
why is gamma in there?
Yes, because so let me tell you what I'm thinking here. Okay, so DGR is the length scale at which relativity is important. Now, you can pick whatever you want. I motivate, like, you can pick the Schwarzschild radius of the remnant. You can pick the Schwarzschild radius associated with the space-time if all the energy was in this. I justify this a little bit more, saying, thinking about the conjecture, which states that if I have energy m and sphere of radius Schwarzschild m, then I have to have a horizon. So now the reason, so here this R Schwarzschild is the Schwarzschild radius of a horizon or of a black hole, in which I have the energy of the remnant. Now, what is the energy of the remnant? The mass of the remnant is the mass of my spacetime minus the energy that I lose through relation of gravitational wave. Here, this is a factor of 4 there unit, it's 14%. So I'm going to ignore it. So my M final is approximately M80M, and M80M is 2 gamma. So now, as you can here, that's why I have 4 gamma. That's it. Comes with it.
Other questions?
You know, I'm curious. Not because if you start with, say, enough charge, you have to make it similar. I mean, not can you do it?
Well, I cannot simulate naked singularities because determinism breaks down. But if you start with naked singularities, you can end up with naked singularities. But you know, that's not particularly interesting. Maybe I can give you a little bit of interesting trivia. Is well, this was with head-on collision. I had similar dreams with I had constituents part. And what I find is that no matter what QRAM you start with, the QRAM of the remnant is going to be always larger, but never larger than 1. So if you start with black holes, you always end up with black holes. If you start with negative singularities, you're going to end up with always negative singularities.
In both the head-on and the in-spiral simulations, what's the largest QRAM that you're able to start with?
Yes.
Like in practical terms.
Yes. So in the head-on case, it was 0.8. And the quantum synchronous spiral, it was 0.7.
What is the
Okay, so there's 2 things there limits this. One is that when you have same charge, as I mentioned, time scales get compressed or expanded, probably expanded, like this. So the more charge you have, the more the time scales are longer. So simulations are longer and expensive. So the number of orbits increases. And for instance, for a distance of like 10 m, without charge, it takes about 2000 m to collide to have a merger. For 0.7, 0.8, it takes like 6,000–7,000. So it gets much more expensive computational. And second, there's some numerical instabilities that have to do with the electric field at the boundary of my simulation domain. That is very difficult to handle. So for the quasi-circular spiral, I couldn't get simulations higher without triggering these numerical instabilities that eventually will contaminate my simulation. So there's some numerics that I cannot control yet that prevent me from running longer and more extreme simulations. For head-on collision, you have something like this. And second, I think the more charge you put, there's more junk radiation, and there's more. It gets a little bit harder to boost the black holes because you're farther from the good initial data. 0.8, I think it's already quite high, and of course you have to increase the resolution because the horizon gets more.
Okay, we're a bit over time, so let's make it a quick question if you can.
How do you put the black hole on the cell side charge?
Yeah.
Into black hole of always
Yeah.
charge.
Yeah. So you can. So in the head-on collision, you can do opposite side. Well, the charge doesn't matter, so you're going to get the same effects. Yeah, for the quasi-circular merger, what you get is you can get the merger. It happens much faster, and so yeah, you can do the simulation. They're much easier. What's much more tricky in the simulation is to make the merger quasi-circular, because when you have opposite charge, you have a strong dipole emission. So if you try putting them in a quasi-circular orbit, they're actually going to end up on an elliptical orbit. So for that case, it gets much more difficult to do is have a quasi-circular merger. But you can definitely do that. It's actually easier to run those type of simulations for various reasons.
Okay.
Thanks, everyone.
Yeah, thanks. Let's thank our speaker again.
If you enjoyed the video, like and subscribe.